So today we will be doing the Section 10 problem set for AP Physics 1. We will start with question number 1. Question 1. Determine linear acceleration of a car that is traveling at 22 meters per second around an 85 meter radius curve. So if I draw a little picture, we know that the radius, that length, is 85 meters. We know the speed is 22 meters per second. So the first thing we notice is that the unit of the speed or of the velocity is in meters per second, which means that is a linear velocity, not a rotational velocity. And in order to find the linear acceleration, we can use the formula for centripetal acceleration, which is AC centripetal acceleration equals v squared over r. So this question is a simple plug in and chug. So if you plug in 22 for v, square it, you get 484 over 85, which comes out to 5.27 meters per second squared, which is your answer. So maybe it'll be easier to do this actually. Alright, so that's question number 1. So question number 2. Flywheel is turned on and attains an angular speed of 45 revolutions per minute in just 4.1 seconds. Find its angular acceleration. So for this question, we can use our kinematic equations. So, we'll use our second kinematic equation, which is v final equals v initial plus acceleration times t. So keep in mind, these equations work for rotational velocities and accelerations and angles if you just divide both sides by r, which will change this into omega final equals omega initial plus alpha t. So now, because our number 2 question is in angular speed, we can use this to find our angular acceleration. We know a flywheel is turned on and attains 45 revolutions per minute, which means that 45 revolutions per minute is the angular velocity final, and 0 is the angular velocity initial. So if we plug in our numbers, we get 45 rev per minute equals alpha times 4.1 seconds, which is our time. So before we calculate this equation, we want to convert revolutions per minute into radians per second, as that is the units that alpha is in. So 45 revolutions per minute, if we divide this by 60, because we get, actually, this is times 1 minute for 60 seconds times, that will convert this to revolutions per second, which times 2 pi radians per 1 revolution. So this will convert into radians per second. When we actually solve this, it actually comes out to 3 pi over 2 radians per second. So we plug this in for our 45 number. We get 3 pi over 2 equals alpha times 4.1. 3 pi over 2 over 4.1 equals our alpha. which comes out to 1.15 radians per second squared. And that's our answer. That's annoying. It's not letting me undo that far back, I guess. Not sure why. So I will manually erase all this. Sorry about the wait. I don't know why I didn't let. Maybe there's a limit on how far back you can go. I'm not going to leave any specs because that's going to annoy me. Alright. Question 3. The Earth rotates about its axis once every 24 hours. Finds the Earth's rotational speed. So this is a converting question. We know that the speed of the Earth's rotation is 1 revolution because it goes around its axis once for 24 hours. So all we have to do is convert it into rotational speed, which is in the units radians per second. So times 1 hour for 3,600 seconds times 2 pi radians per revolution. These cancel and these cancel. When you solve for this, you get actually our final answer is in radians per hour on our multiple choice answer sheet, which means we can skip that step in converting the hours to seconds, and it's just times 2 pi radians per 1 revolution, which gives pi over 12 radians per hour, which is our answer. What the? Oops. Get rid of that. Okay. Question 4. A 2,200 kilogram car drives around a flat circular track with a radius of 30 meters. I'll draw a quick sketch. The radius equals 30 meters. And a car driving around the track. Determine the maximum speed of the car before it begins slipping. If US equals... Okay, so if we think about the forces on the car as it's driving, when it's going around the circle turning like this arrow, there's going to be a centripetal force pushing the car this way, which is determined by AC, as we used in problem 1. That will be the acceleration times the mass of the car. And as friction opposes motion, the friction will be this way. And because we're trying to determine the maximum speed of the car before it begins slipping, we are going to set these equal to each other because that will be when the car breaks friction. So that's like at that moment is when it would start to slip. So that's the maximum speed. So we can say sum of all forces in this, I guess, kind of y direction is 0 as the car, we're saying this is at the point where the car is at the top, because this force is going to be pushing out from the center of the circle. So we're saying the car is located at this location, and that's why the force is going that direction. So in this direction, the car is only moving this way. It has zero acceleration here, so the sum of all forces is 0, which is going to equal this force, which is going to be m times AC, minus the frictional force, which, if you remember, is the constant, which is 0.8 given in the question, times the normal force. And the normal force, in this case, as there's no other forces involved, is just going to be equal to the force due to gravity, which is going to be m times g. So as this minus this equals 0, we can set them equal to each other. Equals 0.8 times mg. The m's cancel. So we get AC equals 0.8 g. And we also know, like we used in question 1, AC equals, after we cancel out the masses, we have AC alone, equals v squared over r. Therefore, v squared over r equals 0.8 g. I will rewrite this as v squared over r, which we know is 30, equals 0.8 g, and g being 9.8. Once we plug g in and solve the equation, we get v equals approximately 15 meters per second, and that is our answer. Moving on to question 5. We'll have to manually erase again. So annoying. Okay. A 0.3 kilogram yo-yo hangs at the end of a 25 centimeter long string. The yo-yo and string are rolled around such that they're rotating at a vertical plane. So this is the yo-yo, we'll say, like the string, and it's being like hurled around in a circle, and this is vertical. The velocity of the yo-yo at the top is 4 meters per second. What is the tension in the string at the top of the path? So when the yo-yo is at the top, it means the string is at the bottom. So the string is going to be holding the yo-yo downwards, and we'll say that it's moving in this direction at 4 meters per second at the very top. So we can say here, the sum of all forces in the y direction, the vertical direction, is going to be equal to 0 because there's no acceleration at that moment, which equals, and if we draw a free body diagram, this will be our yo-yo. The tension is acting downwards. There's the force centripetal acting upwards, as we talked about with problem 4. And there's also force due to gravity acting downwards, which actually helps the tension in this point. So that means it's going to equal force centripetal minus tension minus force due to gravity. We're trying to figure out tension with this question. So if I rewrite this equation with tension on its own side, and we know that force centripetal is equal to the tension plus the force due to gravity once we bring these over to the other side. Tension is going to equal force centripetal minus force due to gravity, which is going to equal m times AC, which, if you remember, is v squared over r, times mg. So when we plug all our numbers in, I'm going to factor out the m for simplicity. M is 0.3 times, and then v the top is 4, so 4 squared over r, which is 0.25. Sorry, this should be a minus g, as we factored out m, which equals 4 squared is 16 over 0.25 is 64 minus 9.8 is 54.2 times 0.3 is about 16.3 newtons. Which is our final answer. So irritating. Uh-oh. That's unfortunate. Okay, well that line's gonna stay there because I don't erase that question. That line's gonna stay there as well. Oh, that's irritating. Accidentally. Okay, we're gonna leave some little bits, I think, just because this is taking a long time to erase. Okay. Question 6. The car is traveling at 12 meters per second on a 52 meter radius banked curve that is covered in ice, so no friction from the banking is necessary to keep the car from slipping. Okay, so for first, I'm going to draw the circle. The radius equals 52 meters. Cars traveling 12 meters per second. We'll talk at the top for simplicity. And it's a banked curve, so if we're looking at it like directly under the wheels of the car, I will call this the bank. This is theta, that angle, and we'll say this block represents the car. So this block is going to be going like this, and it's going to be going around in a circle, and the bank's going to curve like this as well. So this is where the car is going. So this angle theta means that the force due to gravity, which on a flat surface would just be going down, is now going to be split into, if we change our coordinate plane to match up with this, our y direction will now be at an angle and the x direction will be at the angle of theta. So the force due to gravity will be a combination of those two directions. So in order to figure this out, our free body diagram, we have a force due to gravity going straight down, but our centripetal force is actually going out like this at an angle away, and actually this angle is theta for our force centripetal. So if we try to put our force due to gravity into terms of this, we can bring this line down like this, and this angle is also like this angle right here is theta, which means this angle is 90 minus theta, which, if you remember our properties, if the sine of 90 minus theta is the same as the cosine of theta. So I'll use this angle for simplicity to figure out our whether or not to use sine or cosine, but then we'll swap them because we're going to want to find theta and then this angle theta. So in this case, sine right here of this angle is going to be Well, first, actually, I'll rotate this so we can deal with xy. So we'll have our force centripetal going this way, and our force due to gravity is like this, and then the angle we are now looking at is right here. Right, so this angle right here is going to be a combination of one vector going straight down and one vector going left. So so this angle from this diagram we actually know is 90 minus theta, which means this angle is just theta. So sine of theta is going to be opposite this side over the hypotenuse, which if we multiply by the hypotenuse would mean sine theta times force due to gravity equals the force in the negative x direction. So that means the sum of all forces in the x direction, which we know is going to equal 0 because once again we're trying to match them up to find the minimum bank angle necessary, is going to equal force centripetal minus F force due to gravity times sine of theta. Which now we can set them to equal each other, so it's going to be m times AC, which once again b squared over r, equals mg sine theta. M's cancel out. We'll have so v squared, the velocity is 12 meters per second, so it's going to be 12 squared over, the r is 52 meters. Then we're going to be dividing by g times 1 over 9.8 equals sine theta. So we'll evaluate this, plug in your calculator with arcsine, and end up with theta equals 16 degrees. That's our answer. Wow, it's annoying to erase. There's not a bigger size, is there? Doesn't appear so. Okay, question 7. A 2,000 kilogram roller coaster car reaches or is traveling at 18 meters per second as it passes the top of a 24-meter radius loop. So this will be the loop, 24-meter radius, like this length, and it's going 18 meters per second. This way. That's supposed to be an 18 if you can't tell. The force that the roller coaster car exerts on the track of the loop on this point. So, sum of all forces in the y direction, what we're looking at, is going to equal 0. So once again, it's only moving in the x direction, which is going to equal, as it's moving this way, the centripetal force is going to be pushing it up again. So the free body diagram, we're going to have force centripetal, and the force due to gravity is going downwards. And actually, the track is going to be pushing a normal force downwards on the car as well. So that means it's going to be force centripetal minus the normal force minus the force due to gravity. So So this means that the normal force, once we get it going, is going to equal force centripetal minus the force due to gravity, which comes out to be mass times 18 squared, the velocity over r, which is 24, minus, we'll put this in parentheses, it's going to be mg, 9.8, which is g, and so the normal force is going to come out to be, once we plug in all the numbers, 7,400 newtons, which is our final answer. Okay. Halfway there. All right. Question 8. A 2-kilogram yo-yo swings in a vertical circle on the end of a 1-meter string. The bottom of the swing, the yo-yo has a speed of 4 meters per second. What is the force tension? Okay. So the yo-yo is now at the bottom. It's going 4 meters per second. The radius is 1 meter. Okay, so our free body diagram, the yo-yo, force through gravity going downwards. Tension is now going upwards. The force centripetal going away from the center of the circle is also going downwards, meaning sum of all forces in the y direction equals 0 equals tension minus force due to gravity minus force centripetal. So in order to find the tension, it's going to be tension equals m times, put these in parentheses, g, 9.8, plus AC, which is going to be v squared over r, as we've done before, which is 4 squared over the radius of 1. Once we plug this in, we get 52 newtons. That is our answer. Yikes. So close. Okay, question 9. If the tangential velocity of an object moving along a circular path is doubled, then the centripetal acceleration increases by a factor of. So let's think about this. The centripetal acceleration, that is AC, and it's asking about tangential velocity. Tangential velocity means on a circle, if it's moving like this, how fast the object is moving around the circle is the rotational velocity. But tangential velocity is if you choose a point, let's say we choose the top, is if it stops turning, if it just continues in a straight line, how fast it is going in that straight line. So it's linear velocity at that moment. That's what it means by tangential. So we have it equals, it gives us the linear velocity, which means, so we'll do a first is v squared over r, right? So now that's AC1. Let's try the second AC where it says it's going twice as fast. The object tangential velocity is doubled. So this becomes 2v instead of just v squared for r, which equals 4v squared over r. And now we can compare these two. If we do AC2 over AC1, we'll have 4v squared over 1, over v squared over r, sorry, before v squared over v squared of r, which gives us 4. That would be 4 times bigger. Alright, question 10. A 2 kilogram yo-yo, or sorry, 0.2 kilogram attached to a 6.6 meter string is swung in a circle on a horizontal plane. Find the tension in the string if the yo-yo has an angular velocity of 150 revolutions per minute. So what's important to note is it says it is a horizontal circle, not a vertical one, which means gravity is no longer an option. So the sum of all forces in the horizontal direction. Now our plane, we have like a horizontal to the right direction, that is one dimension, and then a horizontal like up and down kind of direction. But it's not up. It's not like in 3 dimensions, it's in 2 dimensions. So gravity isn't a thing. So we'll call this right direction just x, just for simplicity, equals 0, as at this point it will only be having a linear velocity in this one direction. It's just gonna be tension, which is going to be pulling the object to the left at this point. That's tension. And then force centripetal is the only thing pulling it to the right. So minus force centripetal, therefore tension equals force centripetal, which is the mass times AC, which is v squared over r. But the second equation we have for AC is omega squared r, which this is our rotational velocity, which we have in the form of 150 revolutions per minute. If we convert 150 revolutions per minute into radians per second, we get 5 pi radians per second. So this becomes 0.2, which is the m, times 5 pi squared times r, which in this case is 0.6. Once we evaluate this, we end up with about 30 newtons, which is our final answer. Okay. Question 11. Determine the minimum speed necessary for a roller coaster to pass the top of a 12-meter radius loop without falling. Whenever it doesn't give you the mass, and it feels like you're going to need mass, you can assume there's going to be a way to cancel it out. So the minimum speed necessary, if we draw the free body diagram, if it's going, there's a loop like this beneath it, right? Well, it's going to be force due to gravity downward, and a force centripetal upwards. And there won't be any normal force. And the reason why is because it is the minimum speed. So think about it like this. In the other problem we did, where it talked about, that's question 7, where it's talking about how fast it is going. And we figured out the normal force. Question 7, the reason why I was going more than the minimum. Think about if it was going less than the minimum speed, it means the force going up wouldn't be enough to keep it. So it would start falling because force due to gravity would overcome the force centripetal and would start falling downward. Therefore, there wouldn't be any force exerted on the roller coaster because it wouldn't be touching it because it's falling downwards. Well, if we decrease that difference until it's almost 0, really close, but the force due to gravity is still slightly bigger, well, the same thing's going to happen. It's going to be falling, but very slowly because the difference in the force is going to be so slight. So if we make it 0, that's that perfect spot where it won't fall, but it also won't be pushing on the roller coaster. Therefore, there's no normal force. So we can say ball force in the y direction equals 0 equals force centripetal minus force due to gravity. So the mass times v squared over r equals mg, and here's what I'm talking about. The masses cancel out. We have v squared over r equals g, which means root, v equals root gr. And as we have the r is 12 meters, root of g times r comes out to be 10.8 meters per second. That's our answer. All right, final stretch on these 3 questions to go. And the last one is no calculation. The last one is a conceptual problem. Okay, so we'll go 12. Actually, let's erase all of this. Sorry, I don't know why I did that. Anyways, 12. 3,400 kilogram jet is flying at a constant speed as it makes a vertical loop. At the top of the loop, the pilot feels 3 times his normal weight. Okay, so that means that what is saying the pilot feels 3 times his normal weight. Well, first, actually, let's draw the free body diagram. The loop is vertical, so this is going to be the force centripetal, pushing the pilot into his seat, and then we have the force to gravity like this. So sum of all forces in the y direction equals, this time it's not going to equal 0, which we have, it says the pilot feels 3 times his normal weight. So his normal weight, this is for the pilot, not for the jet, but the normal weight of the pilot is mg for him. That's his normal weight. So he feels 3 times his normal weight as he's being pushed into his chair because of how fast he's going. This is going to equal our force centripetal minus force due to gravity, which this is also mg, right? So that means we can now know that force centripetal equals 4mg. And well, force centripetal is going to be m times v squared over r, which equals 4mg. The m's will cancel. And now we have v squared over r equals 4g. We already have the velocities set 170 meters per second, and we know g is a constant. So once we solve, we get the radius of the loop is 736 meters, which is our final answer. All right. Whoa, that was weird. Don't know what happened there. Anyways, okay. Question 13. A car drives around a 75-meter radius curve at a constant speed of 18 meters per second. Car freshener hangs by a string from the rear of a mirror. Determine the angle between the string and the vertical as the car rounds the curve. So the car is driving around this 75-meter radius curve, and it's going 18 meters per second. So the car is, or the car freshener is hanging. This will be the mirror of the car. we'll say, and it's hanging like this. And as the car is moving around, the freshener is going to be hanging at an angle. Well, actually, let me fix this. The car freshener will be hanging at this kind of angle when the car is turning around like this. So at this point, it's going directly to the right, but it's turning. So this car freshener right here is hanging at this angle, theta. It's acting from the vertical, so that's this angle. So, how do we solve this? Well, let's draw a free body diagram. There's going to be this tension on the object, and then mg, and the centripetal force as it's being moved by the car, right? And we know that this theta is the angle we're looking for. So if we make we want to change the tension into these two cardinal directives we have. We know sine theta equals this line over the hypotenuse, so equals the vertical part of this force with the hypotenuse. So that means tension sine theta is going to be the part that goes against gravity, and cosine theta is going to be the part that goes against the centripetal force, meaning as the object will actually be like stationary, these forces will all be equal. That's what the string does. It keeps it in that one location. So in the x direction, it's going to be 0 equals force centripetal minus t times cosine of theta. Oh, I'm sorry, I misread. This actually, I was doing it with this angle. So we're actually talking about this angle right here. So it's not t cosine theta. It's actually t sine theta. Sorry, and then the sum of all forces in the y direction, same idea. 0 equals mg minus t cosine theta. So now what this means, we're going to change this equation to Fc equals t sine theta, which we're going to actually change. We're going to set both equations equal to tension, so over sine theta, and this is going to be mg over cosine theta equals t. So now what we've done is we can set these equal to each other because they both are equal to t. So just doing this for easy sake later. So c over sine theta equals mg cosine theta. So now we can multiply by sine theta on both sides and divide by mg on both sides, and we'll get Fc over mg equals tangent theta. And we'll just do our arctangent. We have these values. Fc will use m times v squared over r as we have all those values. And once we solve, we get theta equals 24 degrees. That's our final answer. And the final question of this problem set. Question number 14. Consider an object of mass m and speed v moving with uniform circular motion at some radius r. If the radius remains fixed but the mass m is tripled and the speed v is half, the centripetal force will change by a factor. Okay, so the centripetal force is equal to m times the acceleration centripetal, which we know AC is equal to v squared over r, right? So we'll say this is FC1, mv squared over r. FC2 is now going to be change. It's the mass is tripled, so 3m times AC, and the speed, we'll say AC2. And the speed, it said, is halved. So v over 2 squared over r, which this becomes v squared over 4r. So it's 3mv squared for 4r, which we can see is 3/4 of this one. Therefore, centripetal force will change by a factor of 3/4. And that is the section 10 problem set. Thank you for watching.